All right, so I should be ready to begin whenever you are.
Okay, sounds good. So let's get started then. Hi everyone, so welcome to SNAPP seminar. First, just some quick regular reminders. So our seminar is being streamed on, oh, sorry, I think I haven't started the recording. Let me start the recording. Okay, as you just heard, our meeting is being recorded and is also being live streamed. So if you don't want your video to appear in the recording or the online streaming, you can turn off your video, or you can just join us from YouTube. During the talk, please mute yourself, but you are welcome to turn your videos on. And if you have questions, you can type them in the chat box. I'll monitor the box, and I'll relay quick clarification questions to the speaker. And the speaker is going to have several quick breaks during the talk, so then you can just ask directly. And at the end, we will have a Q&A session where you can also ask longer questions. Okay, so I'm going to type a link to the slides to the chat box also. So today we are very happy to have Varun Gupta as our speaker. Varun is an associate professor of operations management at the University of Chicago Booth School of Business. So his research interests are in stochastic modeling and optimization, applied probability, algorithm design and analysis, and mechanism design. So he is particularly interested in modeling and the optimization of resource allocation policies for multi-server and distributed systems from a queuing theoretic perspective, and learning and control in non-stationary environments. Varun holds a PhD in computer science from Carnegie Mellon University and a B.Tech in computer science and engineering from the Indian Institute of Technology in Delhi, where he was awarded the President's Gold Medal. So today, Varun is going to be telling us about online control under non-stationarity. So yeah, the floor is yours, Varun.
Thank you so much, Veena. Thanks for the invitation. Please, feel free to turn on your camera so Veena doesn't feel the pressure to keep her camera on. Nice to see faces. Like Veena was mentioning, I kind of like this topic of learning under non-stationarity a lot. So today's talk is a very recent work that we have done on this. So the archive version is sort of still being prepared. It should be up soon. So it doesn't matter if you sort of don't know anything about the LQR system. I didn't know anything either before I began. So I'll kind of go through slowly through all the basics that you need to know for this talk. And before I get into the LQR problem, I just want to give you like a short backstory of how I got interested in this problem more broadly, because it sort of sets the broader agenda, of which this talk is going to be a very minuscule part, but it sort of sets like what's the bigger picture problem that we're trying to address. So there was a paper that I wrote a long time ago with my co-author Anna Radovanovich, where we are looking at this problem of online stochastic bin packing. So in a nutshell, what the problem is the following: that you have an infinite collection of bins of some integer size b, and you will see items arrive IID from some distribution. So items have integer sizes, but you don't know the distribution. So as soon as an item arrives, you have to pack it in one of these bins feasibly. And the goal is that after you've packed n items, you want to use as few bins as possible. Okay. So what we did in that paper was we proposed a simple heuristic, a little bit primal dual back pressure type of algorithm. The crucial bit there was that it was agnostic. It never actively learned the distribution. It just looked at how many bins I have of each level and used that to make its decision. Okay. Again, a bit like back pressure, where you just look at the Q lens to make your decisions. And the advantage of taking this distribution agnostic view was that we were able to also prove results for non-stationary rival patterns. So if the distribution changed over time, we could still prove some regret results. The downside was that if your instance happens to be nicer, if the distribution was actually the same at every time step, we couldn't exploit that. So Siddharth Banerjee gave this talk towards the beginning of this seminar series, where he actually proved that you can get order one regret against the non-anticipative policy if you know the distribution. So those kind of tricks we couldn't play because we are being distribution agnostic. So bigger agenda that sort of arose from this problem and this result was that is there some nice way in which you can combine sort of actively learning the distribution with these sort of agnostic back pressure type of algorithms, so that if the instance is nice, you get low regret guarantees, but if it's not, then you still have nice properties that you get from back pressure, right? And the best is kind of in quotes because it's not clear what it means. But one thing should sort of be clear, that you should not do worse than back pressure. You can ignore everything you've seen so far, data-wise. So you shouldn't be any worse by using an active learning algorithm. So what sort of the right way of combining sort of intentional learning with these policies? So that was the broader agenda within which I started thinking of this problem. In today's talk, I will only focus on the learning part, which is how do you learn to control a non-stationary MDP. Okay, and it's sort of a hard problem. So what we did was we said, okay, let's begin with the simplest MDP, which is very well understood, which is the LQR problem. Okay, so that sort of is the stage for where this talk is coming from. We kind of want to study learning under non-stationary MDPs with continuous state spaces. And LQR was just the first step, but by no means the final word in this space. Okay, so broadly, here's the outline of the talk. I'll first slowly go through what the LQR model is and sort of classical results in the theory of LQR systems. Then I'll first go into some known results on learning and control of stationary LQR problems. In this talk, we'll focus on the non-stationary version. And then I'll also mention a quick note on this orderly least square estimator, which will show up in our talk. Okay, and then I'll end up with some open problems. So that's sort of the agenda. Okay, good. So what's the LQR problem? So LQR stands for Linear Quadratic Regulator. It's a very simple discrete time continuous space MDP. So your state lives in an R to the n. Your actions live in d-dimensional real space. And the MDP is parameterized by two matrices, A and B. A is called the dynamics matrix and B is called the input matrix. And how A and B enter the picture is through these dynamics. So if my state at time t is xt and I take an action u sub t, then my state at next time t is a linear function of my previous state and my control. That's why the term linear, because my dynamics are linear, plus some noise. And in this talk, I'll assume that this noise that gets added is a normally distributed random variable with covariance W, and all the eigenvalues of W are bounded below and above. So I'll assume that. It's not necessary. All you need is its sub-Gaussian, and its eigenvalues are bounded. Okay, so that's the linear part. The dynamics are linear. The quadratic part comes because of the cost. So if I take action if I take action ut and my state is xt, then the cost I pay at time t is a quadratic function of my state plus a quadratic function of the action I take. Okay, so that's linear dynamics and then quadratic cost. I'm only using the A and B matrices are the parameters because in the rest of the talk, I'll assume that Q and R are known and fixed, and therefore I'll assume that sort of implicitly they exist, but I won't add it as the parameter of my problem. Okay, so that's the LQR problem. What's the goal? As usual, you want to minimize the average cost. So in this case, you want to minimize the total cost you pay over an infinite horizon. Okay. Is the basics of the model clear? What the MDP is fully? All right. So that's just the MDP. So what do we know about what do optimal policies look like and what do these cost functions look like? So one classic result is that the optimal policies for these LQR systems fall within this family of linear feedback controllers. Okay, so what it means is that the optimal action at time t is some linear function of your state at time t. Okay. So if I give you some policy k, what can we say about the value function and the average cost? You can write this nice Bellman recursion, which tells you what the optimal or what the average cost under this policy is, and what the bias function is as follows. So here's the recursion. Let me briefly also tell you what the bias function means. So we kind of all know what the average cost means. Just means per time step, what's the average cost I incur. What is the bias function? It basically means the following. So suppose I write this t period value function as a function of my state at time x, and I look at as limit t goes to infinity, the value function for t period problem minus t times the average cost. This converges to some function, some non-degenerate function, which is basically called the bias function. So usually it's denoted by h of x. In our case, what we are saying is that this function is a quadratic function. So it's x transpose px. So that's what we are saying about the bias function. Okay. And P and J solve this Bellman recursion. So if you kind of separate out the terms which involve x and the terms which don't involve x and which are constant, you get this nice recursive equation for the P matrix. And then given the P matrix, you get this nice expression for the average cost. Okay, so one thing to note here is that the P matrix doesn't really depend on the noise covariance W. It only depends on A, B, Q, and R. But the average cost depends still on the noise covariance through this function. Okay. And given that we know how to study a given controller K, how do you find the optimal controller? You just minimize this function by over the matrices K. Okay. So that's all you need to know about the stationary LQR problem when you know the dynamic matrices A and B and the cost Q and R. Okay. So in this talk, we'll be looking at the non-stationary version. So what's the non-stationary version? So now I'll look at a finite horizon problem where my parameters will change over time. So the matrices A and B will change over time and they're unknown. However, I'll assume that the total variation of these parameters is small. In particular, if I look at this total variation, which is the sum of the Frobenius norm of the changes, I'll assume that's small o of t, right? So imagine t to the alpha for some alpha less than 1. Okay. My dynamics and cost are still the same. So my dynamics now just depend on the time, but my cost matrices don't change over time. I'm assuming that the Q and R matrices are still fixed and they are known. It's only the theta parameters which are unknown. Okay. And my goal this time is to minimize the regret. So I want to come up with some policy for choosing these actions u sub t, so that this is my cost. And I want to compare against the optimal policy pi, which is non-anticipative. So it doesn't know the disturbances, the noises W, but it knows the sequence of thetas that let's see. So that's my benchmark. And then just one aside is that this optimal policy pi that we are comparing with will also be linear feedback controller. It's just that the matrix K will change over time as well, right? So there's a nice dynamic programming equation you can write to tell you what this optimal sequence of matrices is. Right. So that's basically the problem setup. We'll assume that the total variation is small o of t, but we don't know v sub t. So we also don't know what this total variation is. Okay. And then we somehow want to get the policy which has the smallest regret cost. So, questions on the problem setup itself? Good, nice. Okay, so here's a short literature review. The problem of controlling a stationary LQR where the matrices A and B are fixed but unknown, it sort of has been studied for a while. The first results came in 2011. The downside of these results were that the dependence on dimensionality was exponential and they were not computationally efficient. So over time, people have come up with better regret guarantees in terms of dependence on dimension, computationally efficient policies, as well as lower bounds. And in a nutshell, basically the result is that you can't avoid order square root regret, and they are algorithms which get you this, right? So that's sort of a nutshell about what's known for the stationary case. Recently, there has been some work for studying non-stationary MDPs, but they assume that the state space is finite and the action space is finite, which is not the setting we are in. So these results are nice, but not quite relevant to what we are doing here. There has also been very recent work on studying LQR problems with non-stationarity, but they sort of look at different flavors of non-stationarity, which are somehow complementary. So there's a sort of very nice paper from Princeton, which look at the case where the matrices A and B are known, but I don't assume that my noise is now IID quotient. So the noise can be even adversarial, but with some total energy, let's say. Okay. The Simchowicz paper looks at the same problem, but they look at a slightly broader class of algorithms, which are called disturbance feedback controller. So here, essentially, because I know the matrices A and B, as I observe the system, I can actually figure out what the disturbances were in the past. And the controller I choose right now is some linear function of some past disturbances. So that's sort of the class of policies they look at, and they sort of adopt some experts optimization kind of view for this. Gautam, who's I think on the call, and Babak have looked at a problem where the matrices are changing over time, but they're known beforehand. What you don't know is the noise, and you assume it's adversarial. So again, there is some total energy, and you kind of want to get optimal regret depending on these factors. There's another paper from Princeton which looks at the case where, again, AT, BT are unknown and changing, but you observe them after time t when you take the action. So you don't know what AT, BT you'll see. You take an action UT, and then you immediately see AT, and BT. Right. So again, in some sense, this sort of becomes an expert problem because you're getting full information feedback about the system that you're dealing with. And then very recently, there's a paper from Adam's group at Caltech, where again, they assume the matrices are changing over time and unknown, but you see k steps ahead of time. So you see the matrices for the next k time step as well as the disturbances for the next k time step. And they prove that the optimal regret somehow scales like some lambda to the k times t. So again, all of these papers look at LQR with non-stationarity, but sort of complementary to the kind of non-stationarity we are looking at in this paper. And one thing you'll see is that all of these papers, most of these are at least within the last 2 years. So it's a very active area of research and lots of open questions here. Okay, good. So that was just a snapshot of what's known in this space. Again, this is a very rapidly changing area, so I'm sure I've missed many papers. Okay, so that's just the basic of the LQR problem. Next, I want to give you like a brief sort of summary of what's known for controlling a stationary LQR problem with unknown dynamics. Because there are many sort of known algorithms. I just want to give you the simplest algorithm that we know of. And one takeaway from this part is the following: that whenever you think of an LQR problem, you should think of it as being a bandit problem where you have linear feedback and quadratic loss. And I'll say more on what this means, but that's sort of essentially the crux of the problem. So what does linear feedback mean? Linear feedback just means that there is a parameter theta which controls my LQR problem. I don't know what this parameter is, but in some sense, when I take an action, I know the state and I know the action. I observe some linear function of this unknown parameter plus some noise. So I see noisy linear feedback for this unknown parameter. Okay, and going forward, I'll denote this XTUT concatenate in column as ZT because that's sort of neater instead of writing these column matrices. And I just write that my feedback is linear. Okay, so that's what the linear feedback part means. What does quadratic loss mean? There's a nice result by Simchowicz and Foster, which says the following: that if the LQR problem you're dealing with has true parameters theta, you estimate these dynamics to be some theta hat. Okay, and then you choose a controller which is the optimal for this estimate. Then there are some constants C1 and C2 such that if your estimation error was less than C1, then the average loss or regret per time step that you will incur would be quadratic in your estimation error. So that's what I mean by quadratic loss. So you are seeing this linear feedback of this unknown parameter. You estimate some theta hat based on that, and your loss is just quadratic in the estimation error. Okay, normally in banded problems, if you estimate in linear banded problems, for example, if you have an estimation error epsilon, then your regret is also linear. But for us, it's quadratic. So that's pretty much the crux of this LQR problem. Okay. So how do we turn this into an algorithm? So we use a very common strategy that's used in these kind of banded exploit problem, which is you sort of explore exploit in phases of doubling durations. Okay, so I have these phases I plus 1, I plus 2, all of them roughly of like 2 to the I duration. And at a high level, what you do is in phase I, you play some controller k sub I, and I'll say more on how you get this controller ki. So you play this controller ki, you get feedback of this linear feedback of x based on your controllers. So based on that, you estimate some parameter matrix theta hat I. The next phase, you use this estimate to create a new controller. Again, you play this for the entire phase, you fix this policy, you estimate a new parameter theta hat I plus 1, and you kind of go on. So next phase, you again use this to estimate the matrix, update the estimate, and so on. Okay. So the question is, okay, how does this estimation happen? We just used ordinary least square estimator. What that means is you say, okay, what theta hat can I pick which minimizes the square distance between what I observe and what I expect to observe. Okay, so that's what's called the ordinary least square estimator. So based on a given phase, you just sort of fit the least squares estimator. And then the question is, okay, what does it mean to play a controller k sub I? You would expect that you should just pick your action to be the matrix or the control that you've estimated times the state. But it actually is necessary to add some exploration noise. Okay, so in this case, what I'm adding is a Gaussian noise, but hitting it with a scaling parameter, which is the sigma I. Okay, and sigma has to be sort of very carefully tuned to be 1 over the one-fourth power of the interval duration, and I'll sort of say why. Okay, but before that, let me tell you, okay, why do we even need this? Okay, why do we even need to add this exploration noise? So the idea is the following, that if I only play this part, if I just keep playing ut equal to kixt, then I somehow cannot distinguish between the following two situations, that my dynamics are either A and B, or they are A minus some delta ki and B plus delta. Right? Basically, whatever x I pay, I'll get the same feedback for either of these cases. And that's why you need to add this exploration noise, so that you can also explore in the orthogonal direction what the changes are, orthogonal to this direction of where I cannot detect what's happening. So that's why you need the exploration noise. And now the question is, okay, why this specific scale? And the idea is somehow usually kind of balance the loss from exploration noise versus the loss from having some estimation error in a parameter. Okay. So first, let's look at what's the total cost of exploration. So for 2 to the I time steps in phase I am sort of adding a sigma I size to my UI. And remember, I pay a quadratic cost for my action in the cost for the MDP. So in some sense, if I add an exploration noise with variance sigma I or sigma I square, then the total cost I pay is the length of the phase times this variance per step. Now, if I add this much noise in my exploration, I'll come up with some variance of my estimator. In particular, the variance of the estimator is inversely proportional to this. The more energy I invest in exploration, the better estimate I have. And remember what I said in the last slide is that my estimation error shows up quadratically in the in the regret. So the variance somehow just shows up linearly, right? So for 2 to the I time steps, my loss would be just 1 over the total variance I inject, which will just be 1 over sigma I square. Okay, so that's the exploration cost versus the cost if I don't explore enough. You just balance these two, and that gives you the right scale of noise to add. Okay, so hopefully, I mean, it gives you some intuition for what's happening. All right. Good. So any questions so far about the algorithm? Okay. Good. So yeah, so this algorithm gives you a regret upper bound of square root t. There's an instance in the paper by Cassel et al. Which also shows you that this is tight. And the instance is basically very simple. It's a one-dimensional problem where your A matrix is basically just a scalar A, which is 1/3, which basically guarantees that even if you just keep taking the action 0, your system will be stable because you're kind of shrinking the size of xt by 1/3. And this matrix B, you randomly pick to either be 1 over t to the 1/4 or minus 1 over t to the 1/4. Okay. And the reason for why 1 over t to the 1/4 kind of was towards the end of last slide, because the size, the standard deviation of my exploration was like 1 over 1/4 power of the phase duration. So that's essentially what's happening. And they prove that for this instance, there is no deterministic algorithm which can have better regret than square root. And the intuition is same, that if you don't learn B, then you pay a loss of 1 over square root t per time step, which is square of this. So the total regret will be square root t. If you want to learn B, then the total variance you want to inject is also square root t. So you kind of can't win. Okay. So that's basically the stationary case. So all you need to know is the fact that for a given time horizon, I sort of can't avoid square root of regret, and this exploration noise when you add somehow should be like 1 over square root of the phase duration. Okay. Good. So that's sort of a high level quick summary of the stationary LQR problem. Maybe a good time to stop and ask questions.
Quick clarification. The theorem said any deterministic algorithm. Does that mean a randomized algorithm might be better? Or?
So the way these things work is like you use this Yau's lemma, where you kind of want to say that no randomized algorithm will be good. And the way you do that is to come up with a distribution over instances and say that no deterministic algorithm will be good against this distribution, which basically also means that there is a deterministic instance against which no randomized algorithm will be better. So they kind of are duals of each other. But yeah, so it also rules out randomized algorithms.
Thanks.
Mm-hmm.
Varun, do you mind repeating the need for exploration? You said you cannot differentiate between A, B, and what's the other one? I didn't get the other one.
Sorry, my writing is quite poor. Yeah, so you can't distinguish between the following: A and B, and A minus some matrix A times K sub I and B plus delta.
Oh, I see.
Right, because what will happen when I hit it with X, basically I'll observe A minus delta Ki plus and then B plus delta times Kix, which will basically just be A plus B Kix, which is also what I observe in this case. So I can't distinguish those. Yeah.
I was confused. I thought delta meant you should look at Ki minus 1, so I was totally lost.
Oh, I see. Sorry.
Thanks.
Mm-hmm.
I also have a quick question on this slide. So you see the cost of estimation error is that is the cost on the like long-term average, right?
So think
Average
of this.
out.
Yeah. So think of this as I use this estimator from phase I, which I will use in phase I plus 1. So what's the cost in the next phase itself?
Yeah, so I was wondering, like, is it like easy to, because then you need, what you need is the average cost for the next phase. It's not the like long-term average, but is there a like a big difference between those two?
So because in the next phase, I'll again add exploration noise, and that will be the one that determines my regret in the phase I+2. So that's why it's sort of we just say, okay, in phase I do something which has implication. So this is also intuitive. I mean, I guess you're right that I can just think of this problem as at every time t, I basically add a noise of 1 over square root t times, let's say, log t, and that will work for the entire horizon. So that you can also think. This just makes it kind of cleaner.
Okay.
Yeah, I don't know if I answered the question though.
Yeah, I think.
We can maybe discuss.
Varun, is there a lower bound that scales with the dimension as well?
Yeah, so this does. I think I forget. So the Simchowitz foster paper, I think, has a dependence which is n times d. So the dimension of x times the dimension of d. I think that's the dependence on dimension, but I'm not quite sure. But the Simchowitz foster paper has that.
I see, and the lower bound scales correctly with the dimension as well.
Yes. The upper and lower bound both have the right dependence on dimension. Yes.
Thanks.
Now, other questions? Good. All right. So now we get to the main object of the talk, which is the non-stationary problem. So I'll first give you like a short lower bound which extends the lower bound for the stationary case, just to sort of give you an idea of what to expect in terms of regret in the non-stationary case. And then I'll show you that there's a sort of popular class of policies where you fix a window size and then just use that to restart learning non-adaptively. I'll kind of show that potentially these algorithms are not useful, and then motivate the adaptive reset algorithm that we use. Okay. So first thing is, okay, what kind of an order of regret should we expect for the non-stationary case? And recall that we're kind of measuring the hardness of this instance by this variation of my theta parameters. Okay. And the theorem that we prove is that if your variation is some t to the alpha for alpha between 0 and 1, so some sublinear polynomial of t, then you basically cannot avoid a regret which scales as the variation to the 2/5 times the horizon to the 3/5. Okay. I guess these, maybe there's nothing sort of deep about these exponents. It's just that the quadratic law sort of gives you these numbers. But let me just give you the instance which gives this lower bound and kind of extends the stationary LQR lower bound, right? So in the stationary case, we saw that for a t horizon problem, you have a regret of square root t. In the variation case, we just sort of paste together many of these instances, many stationary instances. Okay, in particular, you define this epsilon quantity, which depends on the variation and the time horizon. And then you paste together t times epsilon to the 4th many stationary problems, where each of them lasts for 1 over epsilon to the 4th time. And how do you pick these problems? Basically, again, similar to the 1D case. At the beginning of each phase, you pick your b sub t randomly. So remember, the instance here is my a is always fixed to be 1/3, but my bt is non-stationary. Okay, so at is always 1/3. And how you pick bt is at the beginning of each phase, you randomly pick it to be either plus or minus epsilon. And this is exactly what was happening in the stationary case also. The b was like 1 over t to the 1/4, and that's exactly what's happening here. Okay. So what do we expect based on the stationary regret? We know that the regret in each phase would be square root of the phase duration, right? And my phase duration is 1 over epsilon to the 4th. So in each period, my regret would be 1 over epsilon square. I have t over t times epsilon to the 4th many phases. So overall, my regret would be t epsilon square. You plug in this value of epsilon from upstairs, and you get this regret lower bound for the stationary case. Okay. So sort of maybe one thing to note here is that this is different than the regret bound for linear bandits. And again, it's because the cost is quadratic, not linear. Okay. Good. And at a high level, the result would be that we have an algorithm which actually gives a matching regret rate. So we'll present an algorithm in a few slides where we again get the same regret column. So we haven't done too much in terms of the dependence on dimensionality. So I preempt Tom's question in here. Like, I'm pretty sure we are not optimal in terms of the dependence on dimensionality. Okay, so that's just a lower bound. Okay, and how do we maybe come up with an algorithm which gets us closer to this bound? There's a common class of algorithms for linear bandits, multi-arm bandits, where basically what you do is, in spirit, because they're variants, is that you fix some window size tau. Ideally, if you know the variation of your instance, the window size, the right window size depends on this variation. But even if you don't know, then there's sort of recent papers where you can learn the window size as well as you go along. And then you just restart the learning problem every tau step. So you forget everything that has happened so far. You restart the problem. After tau steps, you again forget everything that has happened, and then restart the learning problem. Good. So, and the question is, okay, could similar algorithm work for the LQR problem? Okay, so now there is no algorithm like this that exists. So what we did is, okay, let's just cook up a problem or an algorithm of this flavor and see if that would work. This may not be, I mean, it's clearly not the best algorithm in this class, but it's one reasonable algorithm where we pick this window size tau as well as some exploration noise level sigma. Okay. We split our horizon into these phases of length tau. So basically, as we were doing earlier, you place some policy k sub I in this phase I. Based on that, you estimate some theta hat I. And then using this theta hat I, you come up with some policy k plus I. And the action that you pick in this phase is the controller that you are told you should pay plus this noise. Because that's a very simple class of policy which restarts learning every tau steps and has constant exploration noise per time step. And the result that we have is that there is an instance where even if I tell you what that random instance is, and then you pick tau and sigma optimally, your regret would be at least v to the 1/3, t to the 2/3. Okay, and if I can remind you of the results from the last slide, the lower bound that we proved was this. So this is strictly higher. Okay. It doesn't mean that, I mean, that you this is bad. That will come from the next algorithm where we actually prove that you can attain this regret bound, but sort of shows why that static windows sort of may not be good. And in the next slide, I'll tell you what that instance is and some brief intuition for why static window sizes fail for LQR. Okay. So here's the result again, that there is a randomized instance such that this sort of static window type algorithms don't work. And the instance is a little bit like the 1D LQR problem, where again, I'll sort of fix my A value to be 1/3, and I just re-randomize my B sub T. But this time I'll pick two different scales of B. So essentially what I'll do is that each time T, I'll either re-randomize the choice of my BT to be plus minus 1, so fairly large changes, or with a higher probability, I'll re-randomize my BT to be some epsilon, where epsilon is very small. Right. So overall, if you think of what my instance looks like, it looks like the following. Once in a while, I have these large changes of my B, but most often I have like small changes. Okay. And the reason it's sort of bad is because my cost is quadratic. So these large changes actually hurt me a lot. Whereas in the linear bandit, linear regret case, this doesn't hurt me as much. Okay. So here's sort of the idea in a little bit more formally, that if you only had the second kind of changes, if I only randomize my BD to be like plus minus epsilon, then you would pick a window size which is sort of roughly the gap between these small changes, which would be the T over BT to the 5/6, some number. But what can happen is that maybe I had this window and a big change happened within it. Now I've committed to the window, so I can't really restart right now. And if this happens, then for such window, I basically pay an omega tau regret. So they basically proportional to the window size. And that's bad. And that forces you to pick a smaller window size. So instead of a window size which looks like this, you end up choosing a window size which is smaller, and that's bad. That's a suboptimal window size. That's sort of the intuition, which is because you have large and small changes, committing to a window size is a bad idea. You should have actually detected the change and then restarted as soon as the big change happened at a high level. Okay. All right. So, yeah, any questions here? I guess the devil is in the details and the calculation, but overall, I just want to give you this picture that committing to window size is bad. Okay, and that sort of gives us this intuition for we should probably look for an adaptive restart algorithm, right? So these large changes were hurting us in the last instance, but large changes are also easy to detect. So hopefully, without too much exploration effort, we can detect that a large change has happened, and then we just adaptively restart. And the crucial idea here algorithmically is that we don't know what large means, right? It could be order 1, it could be like t to 1 over t to the alpha. Like, what does large mean? So here we borrow from a very nice paper from a group at USC, which was in the contextual bandit setting. But essentially, the idea is that you start running tests for detecting changes at multiple timescales simultaneously. So you run tests which detect changes of size order 1, half, 1/4, 1/8, all at the same time. Okay, and sort of hope that one of them sticks. That's sort of the high level idea. There is one more assumption that we need for our algorithm. So I'll come to the algorithm in the next slide. But there is one assumption which I don't like so much, but I think that it sort of adds more work than insight getting rid of this assumption, which is we'll assume that someone has given us a sequence of controllers which at least stabilize my system. Okay? And there are results in literature which sort of say how to get this sequence if you don't have them. But for us, we just assume that this is given. Like maybe you have crude forecasts of the dynamics which at least stabilize the system. Okay, so more formally, what do we mean by stabilizing the system? This is what's called a sequentially strong stabilizing controller, which basically means that if I look at any interval tau 1 to tau 2, and I look at the product of these matrices. So pretend that I'm taking the action, which is this externally given controller. This matrix roughly tells me how my expected state evolves. Okay, so if I take the product, it just tells me what's the expected value of my x tau 1 conditioned on the state at tau 2. And what we're saying is that the size of this matrix roughly decays geometrically. So it's sort of exponentially stabilizing the system, these things which are given. Because we'll assume that someone has at least given these to us. Okay, now I'll get to the algorithm at a high level. So what is the actual algorithm that we use? So our algorithm has a few ideas. So the first idea is that you split the entire problem into epochs, where roughly what you want from an epoch is that the total variation of your theta squared should roughly be 1 over the square root of the duration, right? And again, the intuition goes back to what we said earlier, that my sigma square j was roughly like 1 over square root of 2 to the j, right? So that's sort of everywhere, that the squared variation is roughly the same size as 1 over square root of the interval size. It's sort of the right space where you want to at least explore and figure out changes.
So
Yes. So we have like log t factors floating around in the algorithm right now, and I briefly mentioned that towards the end. I think it's possible to get rid of it, but for now we assume that we have we know t, so we can get high probability bounds for everything and then do the analysis. But I feel it should be it's possible to get around it. Okay, good. So, okay, so broadly, our algorithm splits the time horizon into these epochs, and these epochs, you don't know when they end. So they kind of get built as the algorithm goes along. So it's not like I know where all the epochs exist, right? So basically you start an epoch. Now I don't know how long these epochs should be. So again, we do the doubling trick where you create these phases of doubling length. And within each phase, you again do a similar algorithm to the stationary algorithm that I showed you earlier. Right, so you first begin the first phase of this epoch by playing these externally given stabilizing controllers, and you add to them some noise, which is like order 1, because you want to get a good estimate of what the underlying parameters are. Use the OLS estimator to estimate what the dynamics parameters might be. Use that to create another controller, which you then use in the next phase. In the next phase, now you shrink the noise. It's twice as long. So you also shrink how much exploration noise you add per time step. And then you kind of keep going on in these phases of doubling length. Okay, so that's the first idea, which is you sort of have these epochs split into phases. Now, how do these epochs end? So these epochs end when at the end of some phase, you detect that the estimate based on this phase minus the estimate that you had from the last phase is sort of large. The difference between them is large. What does large mean? Again, similar idea as the epoch criterion itself. The squared change should be roughly 1 over the square root of the phase length. When this happens, you say, okay, enough changes happened, let me end the epoch. Now, this is not enough, right? Because as we saw earlier, what could happen is I could have a large change in the middle of a phase. So I should be able to also restart within a phase. And here's where the crucial sort of idea comes in, which is within each phase J, at each time t, you say, you know what? Let me see if a change of scale like 1 over 16th has happened, right? So you sort of potentially have these multiple scales of changes that you want to test against. And in particular, I'm denoting here M as the scale, which basically should mean like phase M. Like I want to detect change which is roughly of the same size as phase N. With probability 1 over square root of 2 to the j plus 10. So that's the probability with which you say, okay, you know what, I want to detect a change of like 1 over square root 2 to the m size. And what you do in that case is for the next 2 to the m time steps, you increase the exploration noise to sigma m. Remember, sigma m was 1 over square root 2 to the m. Based on these 2 to the m steps, you estimate what the parameter is within this window. And if what you estimate is sufficiently different from the last phase, again, you end the block. Sufficiently large now depends on the length of this test block. Okay. And at a high level, this is the algorithm. So we have to do some other bookkeeping because the LQR system may be unstable based on our estimate. So you have to sort of threshold the state and then restart also if the state becomes large and so on. But that's like more bookkeeping. And this is sort of the more interesting part of the algorithm. Okay. So yeah, let me skip the proof sketch because I'm kind of running low on time. Yeah, but any questions on the algorithm itself before I move on? Yeah. Yeah. So that was just yeah, the algorithm at a high level. There was one more thing which I wanted to mention, which is this OLS estimator itself. Like kind of so far said, you know, let's use OLS estimator and it sort of works, but it's not as easy, and this gave us a lot of grief. So I just want to like quickly point out like something to be careful of with using OLS estimators in these non-stationary settings. Okay, so just to remind ourselves what the OLS estimator is. In the first part of the talk where everything was stationary, we also used the OLS estimator. And what does it basically do? It minimizes this sort of loss function, where my loss function, as we said earlier, is the squared loss between what I observe and what I expect to observe if my parameters are theta hat. And if you just expand this xt plus 1 into this, the actual noiseless observation plus noise, you can write a nicer expression for what the estimate would look like, right? So in particular, my estimate solves this nice linear equation. Theta hat times this matrix equals this expression on the right. And I sort of broadly like to think of the first term as the mean of my estimator because it doesn't involve these disturbances W. And the second is somehow adding noise to the estimation error. Right? And sort of one nice thing about the stationary case is that as long as your sort of Z vectors have the sort of span the subspace its full rank, the mean is unbiased, right? So the estimator is at least unbiased, and all you have to care about is the variance. And then you sort of add enough exploration noise. With non-stationary theta, this is not as good. So in the non-stationary case, again, I can write a similar expression for the OLS estimator, where now I have theta t here because my theta is changing over time. And even if all your theta within like these phases are close to each other, what you estimate could have a large bias. So here's a picture to sort of see why this would happen. So imagine I just have two Z vectors, Z1 and Z2, and I'm operating in a 2D space. Okay. And imagine that I have these two theta vectors. So theta 1 at time 1 and theta 2 at time 2. Now, how does the OLS estimator work? The OLS estimator says, okay, I'm basically seeing a projection of these vectors essentially on Z1 and Z2, right? So I don't know theta 1, theta 2. All I know is the projection on these Z1 and Z2. And from that, I want to figure out what the actual parameter is. So if I sort of look at, in this case, what the mean would be, I basically shoot this ray from a projection perpendicular to Z2, and then this other ray from its projection through perpendicular to Z1, it kind of hits here. So I have this huge bias, even though all my theta 1, theta 2 are close to each other. So you have to be a little careful in terms of saying that, okay, if you use the OLS estimator, what are you actually even getting? Because it's not even biased, and the bias would be large. Okay? So what we did was we kind of proved the quality of this estimator from scratch. So basically what we said is, okay, we are given this OLS loss function, and it's kind of hard to deal with. So let's look at this one-dimensional problem where I pick some representative theta bar, which is somehow like, let's say one of the thetas, theta 1, theta t, within a phase that I want to be close to. So let's pick that, pick some direction V, and just look at the one-dimensional loss function if I sort of walk in the direction of V from this theta bar. Okay. And what we say is, show is that the minimizer of this one-dimensional function has a small value for enough V's. So in enough directions, my minimizer is close to this representative theta bar, which is somehow enough to show that therefore the estimator is also close to theta bar. So that's how we do this. And again, we are not optimal in terms of dependence on dimensionality because of this analysis. And the tricky bit here is that this loss function looks very different in V's which lie in the subspace spanned by. So when I take the action X, remember, so if I don't add the exploration noise, then what I observe lies in this subspace. So if my V lies in this subspace, then I have like large variance. So it's sort of easy to estimate. In the orthogonals for subspace, I have very low variance. And my sort of function looks very different in these two subspaces. And that's why you have to do this analysis. You can't just look at the smallest eigenvalue of the Hessian and sort of do work with that. You kind of have to do more fine-grained analysis. So that was just a sort of word of caution on just using the OLS estimator. So that was pretty much the technical part of the talk. I just have like a few open questions in the next two slides. So maybe again, a good point for asking questions.
Varun, I have a question about the lower bound. So in your lower bound statement, you say that alpha is strictly greater than 0, right? So if I set alpha equal to 0, then I end up getting t power 2/3, I believe, as opposed to square root of t in the stationary case. So
yeah, that's still true. So if you have order 1 change, you can still get, you don't get square root T.
Oh, I see. That's what that means. Okay.
Yeah.
I see. Got it. Thanks.
Other questions? Thanks. All right. Good. So let me then briefly end with some open questions. So I've like split the open questions in two parts. One is like specific to the non-stationary healthcare problem that we looked at, and then broadly for non-stationary control in general. So the first thing which bothers me a lot is just the setup of this problem. So we assume that these matrices A and B are non-stationary and unknown, but somehow we assume that the covariance matrix W was known and stationary over time. That somehow seems problematic. You would think that the noise has sort of more uncertainty than the matrices. So it would be nice if we can somehow combine like learning of the dynamic matrices while still somehow allowing non-stochastic noise or non-stationary noise, correlated noise, adversarial noise, some version of robustness to the assumption of noise. So that would, I think, be a nice question. The other thing that bugs me a lot is that we said, let's assume variation is small of t. Now, I don't know what this means in practice. It's okay for theory. Like, I mean, you have a system that's running over time, right? You can't assume that the changes will become slower and slower over time. So a nice result, which also comes back to Yasser's question is, can we look at a setting where my variation is linear in t, but epsilon, which is very, very small. So very small linear function of t, and then prove a regret guarantee, which looks like epsilon to the 2/5 times t, right? So essentially, this is sort of like the Vt to the 2/5, t to the 3/5 result, but with V replaced by epsilon t, right? So can we get something like this? Right now, we don't have this because what we have are like log factors in front of this. And this will actually keep growing with t, right? So we don't have this right now. I think it's possible. The other thing which I also don't like is that so far we have summarized the hardness of the instance in the single number, which is the total variation. But for a given VT, you can again think of very different instances with very different performance of algorithms. So is there some sort of notion where we can talk about, I have an algorithm which for this instance gives me the optimal regret, right? And it could be a finer grained dependence on the instance than just VT. And we have some thoughts on in that direction as well. The other thing which I think is a nice open question is, can we think of some model-free version of this problem? So right now, we are learning the dynamics and then choosing an optimal controller based on the learned dynamics, but can you just directly learn the controller itself without ever learning the dynamics? So this Graudu et al. Paper that I mentioned earlier does this, but they assume that you observe the dynamic matrices after you take the action. So this is almost like an expert setting where you can do this thing. In a banded setting, it's not as clear. So there are some sort of papers in the linear banded setting which do this, but I think that's also a nice question. And then one other question is, right now we have like these hard restarts where we start using the stabilizing controller and we start learning. Seems too harsh. Is there sort of more slicker sliding window type algorithm? So the problem here is that the analysis doesn't sort of work well with changing your policy multiple times. So there is a term in the regret, which directly is the number of times your policy changes. And this screws up with that part of the term. Okay, so this is just for the LQR problem. And more broadly, sort of going back to the agenda from the beginning of this talk, how should you combine learning and sort of these back pressure type agnostic policies? So there is some work of Michael, Neely, and Longbo Huang in the space, but I think more can be done, even in a queuing theoretic setting. And there's a very nice survey by Neil and Kwong, I think it may be in the pipes, but should be in the upcoming informs, where they kind of look at like learning and back pressure type of control in a queuing setting. And they sort of, I think, give a good overview of what's known in this space and where you can use learning, where you can use back pressure type techniques. Okay. The other direction, which I think is very promising, is to actually exploit forecasts. So can you exploit noisy forecasts to plan better? And how should the uncertainty in this forecast affect how you use these forecasts? There's a very nice a few papers by Adam Wayman's group in Caltech, which look at these flavor of problems, which I like. And then finally, neural networks are becoming popular for control of queuing systems. Jim gave a talk here recently. Now imagine my queuing system is non-stationary. How do you sort of combine these policy approximation using neural networks with some sort of non-stationarity, right? And there's a sort of nice meta-RL technique which says how you can transfer what you learn for one activity to another. I think a natural candidate is just like a queuing system, but it's non-stationary. So it's the same task, but where the parameters change. So can I somehow still use these techniques? So I think all of these are sort of very, I think, ripe questions that we can start answering. And sorry for going over time. I'll stop.
Thank you for the great talk, Varun. So do we have questions from the audience?
Maybe one question, if that's okay.
And you go ahead.
Hi, put my video on. Hi, everyone. What extent are these things sort of dependent on doing ordinary least squares? Was one question. Do you have to use ordinary least squares? Could people just use like a kind of gradient descent type argument? I mean, I know a lot of these are based on more like sort of like linear UCB and things like that, and so then that's a kind of least squares type of argument. I wasn't aware of much literature that did that.
So for LQR, so in the non-stationary case, I don't know so much. Okay, so the gradient descent type of algorithms, the ones I have seen are a little bit like these using experts for bandits, where you use 1-point gradient estimators and then use that.
Okay, yeah.
The advantage there is that you don't have to assume variation in budget. So there you can directly compare with benchmarks where the policy changes few times instead of the parameters, right? I don't know of a sort of good unifying result which says that those will also work in the case where variation is small. So I think there's a difference, like different class of policy, different classes of regret results which are proved with these things.
Mm-hmm.
Coming to LQR itself, you can use non-OLS based algorithms. So one of the efficient algorithms, or the first efficient algorithms in this space, was actually using SDPs to directly optimize the covariance of X. So you sort of observe some things and then you say, okay, let me directly optimize the covariance of X because that's my cost. And then from that back out a control, which is a little bit like UCB also.
Yeah, because I think sometimes in time series, you can do like a weighted ordinary least squares where you might weight towards the current time a bit more and things like that.
So that's, yeah, weight UCB does that in a UCB setting.
Yeah, okay, fine. Okay. The other thing is in your algorithm, I guess it's a little bit, maybe I'm relating everything to linear UCB, but linear UCB, you kind of got like a confidence interval, eventually your parameter estimate belongs to that set. And once it's within some given region, you'll kind of find the algorithm's going to work. And I guess it's like that, your algorithm, you're basically saying, well, once it's left this region, then I don't have confidence in the algorithm anymore. We need to kind of reset, if you see what I mean. Yes. That's sort of what I was wondering.
Yes.
Yeah. Okay.
The thing with Lin UCB, so recently there were like these, there was a paper on like regret for the UCB algorithm, and there were like a few bugs because somehow Lin UCB, it's not clear that the OLS estimator used by Lin UCB has a small bias because they don't explicitly explore.
I understand. Okay, yeah, that's a good point. Yeah. Okay, great. Thanks. Good talk.
Hey, Chongming, go ahead.
Hi, Varun. Thank you for the nice talk and the nice work. I have a question about how you schedule the detection test. So here the M can be different value from 0, 1 to up to J minus 1, right?
Yes.
Yeah. And so do adaptively increasing M, or I'm not, I'm a little bit confused how you,
So independently, so at each T, for each M, sample a Bernoulli with this probability. Okay. And then you could start multiple of these phases could be going on in parallel. You
Okay.
just pick the noise for the most conservative. So whatever M is the smallest.
I
So you
see.
just
Kind of like multi-scale detection in parallel going on.
yes.
Okay. Okay. Then I think this similar to the results from the recent paper from the same USC group, Hyperroll. They recently extend this type of approach for a cluster of non-stationary problems, from band-aid to episodic MDP to infinite horizon average cost MDP. But they didn't consider linear quadratic regulator problem you consider here. So
Yeah.
I think your work kind of like filling in the gap and completes the story. Yeah.
Yeah, I think eventually the only thing that happens here is that like the cost is quadratic instead of linear. It's almost like that. So a few parameters change here and there, and the LQR stability adds a little bit of messiness to analysis, but at a high level, yeah, it's almost similar.
Thanks.
Thanks, Ronnie. Gautam, go ahead.
Yeah, I had a quick question. You talked a lot about minimizing the expected regret between the your online policy and the non-anticipated policy. Can you prove any concentration results about how well how well the online expected cost sits around the expected cost of the offline?
I think it's possible. We haven't tried doing that, but I think it's possible.
Yeah. I'm also curious if you know. So you made this bounded covariance assumption on the noise, and I'm curious. Does the regret scale linearly or superlinearly in the variance of the noise?
I would say so. Again, I think we haven't optimized that dependence. So I think right now our analysis probably shows superlinearly, but I don't know if there's a lower bound which says that it has to be superlinear.
It wouldn't surprise me if the lower bound actually is superlinear, because since this is sort of non-stationary, if you have a mistake, it sort of blows up exponentially in time, right? So if there's noise, but potentially.
I see. We can talk about this. I mean, my prior is that because it sort of enters linearly in everything.
Oh, okay. Well, you might be right.
But I mean, yeah, I should go back and we can talk later.
Sure. Okay. Thank you.
Thanks, Gautam.
Okay, any more questions? Okay, if not, let's thank Varun again for the great talk. Yeah, thank you.
Thanks for the invitation. Thanks everyone for attending.
Yeah, thank you, Varun. Bye.
Thanks.